This is Unit 8, Stoichiometry. By the end of this unit, you will be able to determine mole ratios, determine the mass relationships between reactants and products using stoichiometry, determine which reactant is limiting in a reaction, and calculate percent yield. Stoichiometry is derived from the Greek stoichion, meaning element, and metron, meaning measure. This is the term that we use to refer to all quantitative aspects of chemical reactions. What is stoichiometry? Stoichiometry is the field of chemistry that deals with the measurement of reactants and products using balanced equations and dimensional analysis. Stoichiometric calculations are the molar relationships between the reactants and products in a balanced equation. In other words, stoichiometry adjusts your chemical recipe to just the right size. Stoichiometry. So let's think about a sandwich for a moment. If we're making the perfect BLT, we need 2 slices of bread, 6 pieces of bacon, 3 pieces of lettuce, 4 slices of tomato, and 1 tablespoon of mayonnaise. So let's write this recipe as a chemical equation. Remember, the subscripts tell you how many of each element are in a formula, and the coefficient tell you how many of that formula are needed in a balanced equation. So we have 2 bread plus 6 bacon plus 3 lettuce plus 4 tomato plus 1 mayonnaise yields the perfect sandwich. This shows us how many of each element we need in order to make one sandwich. But what if we wanted to make 8 sandwiches? How many of each thing would you need? So you look at the balance numbers, or the coefficients. So if we wanted 8 sandwiches, we would look at the ratio between the sandwich and the bread. So for each one sandwich, we need 2 slices of bread. So for bread, we would need 16 pieces. What if we only had 3 pieces of bacon? How many sandwiches could you make? So if we had 3 bacon, now we would look at the coefficients between bacon and the sandwich. So one sandwich needs 6 pieces of bacon. So we could make 0.5 sandwiches, or half a sandwich. Now let's try it with some chemistry. In chemistry, we use moles to predict the amount of reactants consumed and the amount of products produced by a reaction. The relationship between any 2 compounds in a balanced reaction is a mole ratio. So what is the mole ratio of iron to carbon? So iron has 4, carbon has 3. So for every 4 moles of iron that are produced, 3 moles of carbon are consumed. So if we're looking for the mole ratio of iron 3 oxide to carbon, for every 2 moles of iron 3 oxide, we're going to need 3 moles of carbon. And the last one, carbon dioxide to iron. So we have 3 moles of carbon dioxide for every 4 moles of iron. Let's look at how these are used in stoichiometry. When hydrogen gas reacts with oxygen, water is produced. How many moles of hydrogen are needed to react with 8 moles of oxygen? So our first step is to write the formulas for the reactants and the products. Hydrogen plus oxygen yields water. Now we need to balance the equation. So we have 2 oxygens on our reactant side. We need 2 on our product side. That gives us 4 hydrogens. So we need 4 hydrogens on the reactant side. Now we use dimensional analysis. So write the mole ratio of the 2 reactants or products that you're looking for. So 2 moles of hydrogen react with 1 mole of oxygen. Then we're going to use the conversion factor for the dimensional analysis. So we had 8 moles of oxygen. We're using our conversion factor to get to hydrogen. So our 2 moles of hydrogen go at the top, the 1 mole of oxygen at the bottom, and then we can solve. So it would take 16 moles of hydrogen. How many moles of calcium chloride are consumed if 3.3 moles of sodium chloride are produced? So we have 3.3 moles of sodium chloride. We're looking at our mole ratio. So it's a 6 moles to 3 moles of calcium chloride. So our 6 moles of sodium chloride go at the bottom. The 3 moles of calcium chloride go at the top. And we get 1.65 moles of calcium chloride. Okay, how many moles of iron oxide are produced if 4.56 moles of oxygen are consumed? So we're looking at oxygen and iron oxide. So for every 7 moles of O2, we produce 2 moles of iron 3 oxide. We started with 4.56 moles of oxygen. We're trying to get to iron oxide, so our 2 moles of Fe2O3 over the 7 moles of oxygen, so we would get 1.3 moles of iron 3 oxide. How many moles of sodium chloride can be produced with 0.123 moles of sodium phosphate? So we need our ratio between sodium phosphate and sodium chloride. So for every 2 moles of sodium phosphate, we're going to produce 6 moles of sodium chloride. So we started with 0.123 moles of sodium phosphate. We're trying to get to moles of sodium chloride. So our 6 moles of sodium chloride at the top, the 2 moles of sodium phosphate at the bottom, and when we solve, we would get 0.369 moles of sodium chloride. So when we're in a lab, you can't measure moles directly. So you're most likely going to use mass or volume. No matter what you start with, mass, volume, or particles, you have to convert to moles first. The only way to compare products or reactants is through moles. Think about it like a mole bridge. The only thing that can get across the bridge are moles. So look at the example below. How many grams of lead-4 sulfate are needed to make 5 grams of lead-4 nitrate? So the first thing we need to know are the molar masses of lead sulfate and lead nitrate. If you've forgotten how to find the molar mass, watch the video on moles. So we're starting out with 5 grams of lead nitrate. Our first step is to get to moles. So we need the molar mass of lead nitrate. So 1 mole of lead nitrate is 455.216 grams. Now we can use the mole ratio. So our ratio between lead nitrate and lead phosphate is 1:1. So for 1 mole of lead sulfate, we'll use 1 mole of lead nitrate. That gets us moles of lead sulfate, so now we can use the molar mass to find how many grams. So 399.312 grams of lead sulfate for every 1 mole of lead sulfate. So when we solve, we get 4.39 grams of lead sulfate would be needed to make 5 grams of lead nitrate. The next question, we're looking for moles of lithium sulfate from grams of lead sulfate. So we have 3.25 grams of lead sulfate. So our first step is always to get to moles. So 1 mole of lead sulfate is 399.312 grams. Now we can use our mole ratio between lithium sulfate and lead sulfate, which is 2:1. So for every 2 moles of lithium sulfate that is produced, we use 1 mole of lead sulfate. So we end up with 0.0163 moles of lithium sulfate. Okay, try the last one on your own. So remember, The only thing that can bridge between reactants or products are moles. So no matter what you start with, volume, mass, or number of particles, you have to get to moles first before you can compare products and reactants. Limiting reactants. Most reactions have more than one reactant. The reaction will continue until you run out of one of the reactants. Whichever reactant runs out first is the limiting reactant. So let's look at the perfect BLT again. If we had 22 pieces of bread, 73 pieces of bacon, 19 pieces of lettuce, 48 slices of tomato, and 14 tablespoons of mayo, how many perfect BLTs could you make? So we're going to divide each of the things that we have by their coefficient. So if we look at bread, we had 22 pieces of bread, but we need 2 for each sandwich. So we could have a total of 11 sandwiches if we look at just bread. So for bacon, 73 divided by 6, we could make 12 sandwiches. With lettuce, we could only make 6. With tomatoes, we could make a total of 12 sandwiches. And with mayonnaise, we could make 14. So the one that would limit us is the lettuce. So our ingredient that ran out first is lettuce. So that is your limiting reactant. Everything else is in excess. So how do you find the limiting reactant? Your first step is to write the balanced equation. Then find the number of moles of the first reactant. Step 3, divide by the balanced number. Then repeat this for all of the reactants in the chemical equation. Step 5, the smallest number is going to be the limiting reactant. So if we had 3 moles of A and 5 moles of B, what is the limiting reactant? We have 3 moles of A and 5 moles of B, so we divide by our balance number. So our coefficient for A is 2, the coefficient for B is 4. So we get 1.5, and for B, 1.25. So we look at both of them. The one that is the smallest is limiting. So for this one, B is your limiting reactant. So if you're given the mass or moles of all of the reactants, assume that the problem is limiting. Once you find the limiting reactant, all of the other reactants are in excess. So if there are 25 grams of magnesium burned in a sealed container with 35 grams of oxygen, which reactant is limiting? So we have 25.0 grams of magnesium and 35.0 grams of oxygen. So our first step is to get to moles. So we're dividing by the molar mass. So we'd have 1.02 moles of magnesium. We're going to do the same thing for oxygen, divide by O2's molar mass. We have 1.09 moles of oxygen. Now we look at our balanced equation. So 2Mg plus O2 yields 2 MgO. And now we're dividing by our balance numbers. So the balance number for magnesium is 2, and for oxygen is 1. So we would have 0.51 for magnesium and 1.09 for oxygen. So magnesium is what's going to limit the reaction. So the question asks us how much magnesium oxide can be produced. Much means that we're looking for grams. So we know that magnesium is what's limiting. So we're going to start with 25 grams of magnesium. Remember with Stoic, our first step is to get to moles. So 1 mole of magnesium, 24.305 grams. We use our molar mass. Now we can use our balance numbers. So we have 2 magnesium that are used for every 2 moles of magnesium oxide produced. So 2 moles of MgO over our 2 moles of magnesium. Now that we have moles of magnesium oxide, we can use the molar mass to find how many grams. So the molar mass of magnesium oxide is 40.304 grams per mole. And we get 41.5 grams of magnesium oxide. Assuming you start with 20 grams of iron 3 phosphate and 75 grams of calcium carbonate, which one is limiting? So our first step, we already have the balanced equation, so our first step would be to get grams to moles. So 1 mole of iron 3 phosphate is 150.815 grams, and 1 mole of calcium carbonate is 100.086 grams. So we had 20 grams of iron phosphate. We need to get 2 moles. So we're dividing by our mass number. So we get 0.1326 moles. We have 75 grams of calcium carbonate. We'll do the same thing, divide by the molar mass of calcium carbonate. So we have 0.79355. Now we're dividing by our balance numbers. So the balance number for iron phosphate is 2. So we would have 0.066. And our balance number for calcium carbonate is 3. So we have 0.2497. Now we compare, and our smallest number is iron phosphate, so our limiting would be iron 3 phosphate. And percent yield. Percent yield compares the amount of product that is actually made to the amount that you calculate could be made. The equation for percent yield is actual yield divided by theoretical yield times 100. The actual mass is what you determine in the experiment, so what you did in the lab. The theoretical is the mass that you calculated using stoichiometry. Percent yield tells you how well you implemented the lab techniques. It also makes you consider why you did not produce the theoretical yield. Very low yields or yields greater than 100% indicate a problem with your lab technique or the calculations. So you calculate that a reaction should produce 38.0 grams of sodium chloride. You collect 27 grams when the reaction's finished. What is the percent yield? So we need to know our actual and our theoretical. The actual is what you collect, so 27.0 grams. Your theoretical is what you calculate, so 38.0 grams of sodium chloride times 100, so you should have 71.05%. Look at the next one. You collect 12.2 grams of lead chloride in an experiment. You calculate you should have had 14.2. So what is your percent yield? So our actual is 12.2 grams. The theoretical is 14.2 grams times 100. So your percent yield is 85.91%. So to find percent yield, you may have to calculate the theoretical amount of product that's produced. So what is the percent yield of the following reaction if 40 grams of magnesium are used and 2.2 grams of hydrogen are produced? So we know our actual yield, we have 2.2 grams of hydrogen. We need to find our theoretical yield. So we started with 40.0 grams of magnesium, and we're calculating how many grams of hydrogen we should have made. So our first step is to divide by our molar mass. Now we use our mole ratio. It's 1 to 1. So for every 1 mole of hydrogen that is produced, 1 mole of magnesium is used. And then we can get 2 grams of hydrogen by using our molar mass. So 2.016 grams of hydrogen for every 1 mole of hydrogen. So we should have made 3.3178 grams of hydrogen. So our actual yield is 2.2 grams divided by our theoretical, 3.32 grams, times 100. So we have 66.278 7%.